When galaxies collide, their majestic spiral arms lose shape, and something entirely new begins. Without the ongoing rotational momentum that sustains those spirals, the resulting galaxy will transform into a more rounded and symmetrical structure. Along with this shift in form comes a change in color. The brilliant blue regions that once birthed stars in the Milky Way and Andromeda will gradually fade, giving way to a warmer, golden hue. This marks the passing of time, as the youngest and hottest stars burn out, leaving behind cooler, longer-living reddish ones. In anticipation of this grand cosmic union, scientists have already coined a name for the resulting galaxy, Milkomeda. Though it will retain echoes of both parent galaxies, this newborn titan will be more expansive. At its heart, it will likely host an immense black hole, formed when the supermassive black holes of the Milky Way and Andromeda spiral into one another and fuse, generating a gravitational behemoth at the core. Picture a distant future. Earth's solar system, aged by billions of years, will orbit a sun that has changed dramatically. Within 5 billion years, our sun is expected to swell into a red giant, rendering Earth uninhabitable. Yet if humanity, or any intelligent descendants, endures and ventures into space, the galactic merger could spark fresh opportunities in the cosmos. A dramatic influx of gas from Andromeda will breathe new life into star formation, potentially giving rise to habitable worlds. The rearrangement of stars and planetary systems will reshape interstellar terrain, possibly creating more navigable paths for travel between stars or even galaxies. Despite the scale of this event, actual collisions between stars will remain exceedingly rare due to the immense distances that separate them. Instead, gravity will be the primary architect of change. The powerful gravitational forces at play will alter the trajectories of stars, remapping the galaxy's structure. Some solar systems could be flung into new orbits, and others might be ejected entirely, perhaps even our own, which could drift deeper into the new galactic core or be hurled into the void of intergalactic space. Simulations offer a glimpse into the calm after the storm. Once the merger settles, Milkomeda may enter a period of relative tranquility. Yet others suggest it might continue to evolve, merging with additional nearby galaxies as cosmic time marches on. Meanwhile, the ever-expanding universe will stretch the distances between galaxies, slowly unraveling the threads that once connected them. In that far-off era, galaxies now visible in our night sky will have receded beyond reach, the light stretched into invisibility by cosmic expansion. Only those that have already merged or remain gravitationally bound will still be visible. Milkomeda will become a solitary beacon, a grand island galaxy adrift in a sea of growing darkness. Look deeper into the universe, and you'll see this isn't a unique story. Galaxies are merging everywhere, at every stage, from initial encounters to fully blended ellipticals. By observing these cosmic interactions, astronomers can fine-tune their simulations, allowing us to better understand the powerful dynamics shaping our universe. Even if humanity won't witness this spectacular event firsthand, our ability to simulate the future offers a preview of a drastically changed night sky. Comparing the anatomy of Andromeda and the Milky Way reveals insights into their destiny. These two giants are the crown jewels of the local group, a galactic family of over 50 members. Each one contains billions of stars, vast spiral arms, and a supermassive black hole at its heart. But their differences are just as striking. Andromeda's diameter stretches about 220,000 light-years, while the Milky Way spans between 100,000 to 160,000 light-years. Surprisingly, despite its smaller size, the Milky Way may actually be more massive, thanks to its dense core and an extensive halo of dark matter. These distinctions open up questions about how galaxies grow and evolve. Andromeda's broad disk suggests it has cannibalized more small galaxies, adding their stars and material to its structure. With around 1 trillion stars, Andromeda boasts more than double the stellar population of the Milky Way, which contains between 200 and 400 billion stars. This may reflect greater star-forming efficiency or a more active history of galactic mergers. But when it comes to star formation today, the tables turn. The Milky Way remains vibrant with stellar births, as evidenced by its bright blue clusters and nebulae. Andromeda, in contrast, appears to be entering a quieter phase. Its central bulge is more prominent, filled with older, redder stars packed into a dense core. This bulge tells a story of violent interactions, massive mergers in the past that funneled gas into the center, sparking intense starburst activity. By contrast, the Milky Way's core, though similarly dense, is less pronounced, suggesting a more stable past or a different evolutionary path over billions of years. At the very core of Andromeda lies M31*, a black hole estimated at 140 million solar masses. The Milky Way's central black hole, Sagittarius A*, is a much lighter heavyweight at around 4 million times the mass of the Sun. Andromeda's massive black hole hints at a turbulent history, possibly one where multiple smaller black holes were consumed in its growth. This immense central black hole exerts powerful gravitational influence, stirring the stars around it into a more energetic state. As both galaxies spin, their spiral arms sweep through space with elegance. Andromeda's stars race ahead at about 250 kilometers per second, faster than the Milky Way's average of 220 kilometers per second. This discrepancy likely arises from differences in stellar mass distribution, with Andromeda's dense bulge and populous arms contributing to its greater rotational speed. Despite these differences, the two galaxies share essential traits. Both are barred spirals, with elongated central bars that help funnel material inward, fueling new stars and feeding their central black holes. These structures are common among spiral galaxies and often arise from gravitational interactions over time. Their satellite galaxies also reflect this blend of similarity and difference. Both are surrounded by a host of companions, dwarf galaxies and globular clusters. The Milky Way, for instance, is accompanied by the Large and Small Magellanic Clouds and the Sagittarius dwarf galaxy, the latter currently being torn apart by gravitational tides. Orbiting giants often leave traces of their past, and Andromeda is no exception. Nestled around it are companion galaxies like M32 and M110, which bear the telltale scars of ancient gravitational encounters. These satellites don't orbit at random. Recent findings suggest they move in a surprisingly organized plane, unlike the Milky Way's satellites that scatter more freely. This unusual alignment hints at vastly different formation histories between the two galaxies, shaped by cosmic events long since past. Much of Andromeda's true beauty is hidden beneath a cosmic veil. Thick clouds of interstellar dust obscure its intricate structure from view, scattering visible light and concealing vast swaths of the galaxy. It's as if the universe has drawn a curtain across one of its grandest masterpieces. But where our eyes fail, infrared vision reveals a hidden world teeming with complexity. Infrared light becomes the astronomer's lantern in this darkness. It slips through the dusty barriers, illuminating details invisible to traditional telescopes. Through these eyes, Andromeda is transformed. What once looked like dark streaks across its spiral arms, mere shadows in visible light, are unveiled as glowing dust lanes, tracing the galaxy's very skeleton. These radiant filaments are more than beautiful, they are vital. They cradle the cold dust and gas that serve as the raw ingredients for stars. By tracking these luminous veins, scientists can map where future stars will form, long before they shine in visible light. In this way, infrared astronomy lets us peer not just into the past, but also into the future. At the galaxy's heart, light overwhelms in visible wavelengths. The combined blaze of millions of stars near the core creates a featureless glare, masking the drama playing out within. But infrared telescopes pierce this brightness, revealing a dynamic, rotating disk of stars spiraling around a supermassive black hole. Where once we saw only a luminous blur, we now see motion, structure, and tension. Stars hurtling through space, their paths bent by immense gravity. Many of these stars are red giants, aging suns that glow brightly in the infrared. Their light becomes a beacon, allowing astronomers to trace the flow of time itself through the galaxy's stellar population. As galaxies dance and collide, they leave behind trails of debris, wispy streams of stars, dust, and gas. These tidal tails can stretch across vast expanses, often too faint to spot in visible light. But infrared detectors can catch their warmth, like footprints still glowing from the fire of a cosmic encounter. Infrared also shines a light on the faintest members of the galactic family, brown dwarfs. These failed stars lack the mass to sustain nuclear fusion, rendering them nearly invisible in optical light. Yet they radiate softly in the infrared, revealing a ghostly population of substellar objects scattered throughout Andromeda. These dim wanderers add another piece to the puzzle of how stars, and almost stars, form and evolve. But not all cosmic secrets lie in light. Some arrive as whispers in the dark, radio waves that carry messages from the hidden machinery of galaxies. Where visible and infrared light reveal stars and heat, radio waves paint a picture sculpted by gas clouds, magnetic fields, and echoes of ancient cosmic events. Among the most powerful tools in this domain is the hydrogen line, a faint radio signal emitted by neutral hydrogen atoms. Tuning into this 21-centimeter wavelength, astronomers can trace vast rivers of hydrogen gas coursing through Andromeda. These radio maps show that the galaxy's disk stretches far beyond what we can see, its outer reaches blending seamlessly into the intergalactic medium. Radio waves reveal not just shape but force. As charged particles spiral through magnetic fields, they emit a signature known as synchrotron radiation. This glow maps out Andromeda's magnetic field, an invisible scaffold guiding the flow of gas and the birth of stars. It's a hidden force with a powerful hand in shaping the galaxy's evolution. Among the stars, some shine not with light, but with rhythm. Pulsars, rapidly spinning remnants of dead stars, send out beams of radio waves like cosmic lighthouses. Even across the vast gulf of space, these pulses reach Earth. Detecting them in Andromeda offers a rare glimpse into the life cycles of stars beyond our galaxy. The core of Andromeda also pulses with radio energy. Though its central black hole is less active than some, it still sends out a steady stream of radio emission. These signals come from charged particles caught in magnetic maelstroms near the event horizon. By listening closely, astronomers can learn how the black hole feeds and how it shapes the region around it. Elsewhere in Andromeda, mysterious radio sources appear without visible or infrared counterparts. Some are likely remnants of supernovae, the shockwaves energizing gas and dust to emit in radio wavelengths. Others may be stellar nurseries where massive newborn stars light up their surroundings with bursts of radio energy. Yet many of these sources remain puzzles. Their faint signals demand more sensitive instruments and more time under the radio telescopes. Each observation chips away at the unknown, revealing the galaxy's hidden rhythms, one frequency at a time. And then, there's the question that reaches beyond science into imagination. Could something, or someone, be trying to speak? Though no signals have yet hinted at intelligent life, astronomers have pointed their antennas at Andromeda, listening for patterns in the static. So far, only silence. But the search continues, for even the faintest anomaly in the background noise could one day become a signal from the stars. Amid the silent expanse of space, astronomers continue to listen, attuned to the faint whispers Andromeda sends across the cosmic void. Some of these efforts are more speculative than others, driven by the hope that intelligence may not be unique to Earth. As part of the broader search for extraterrestrial intelligence, SETI, scientists have aimed sensitive radio telescopes at Andromeda, operating under a compelling assumption. If advanced civilizations exist within its boundaries, they may harness radio waves for communication, much like humans do. Looking ahead, the upcoming square-kilometer array telescope promises to revolutionize what we can detect. With unprecedented sensitivity and resolution, it will map Andromeda's magnetic field in extraordinary detail, pick up fainter hydrogen emissions, and potentially uncover entirely new sources of radio waves that have so far eluded detection. Through radio astronomy, Andromeda doesn't just shine, it whispers. It reveals quiet, cosmic truths to those patient enough to listen. But Andromeda's secrets are not limited to light alone. In rare and extraordinary instances, it can also bend the very fabric of space itself, becoming a natural lens through which the early universe can be seen. Gravitational lensing, one of the most powerful tools in modern astrophysics, allows massive objects like galaxies to magnify and distort the light of more distant sources behind them. In this role, Andromeda acts as a kind of cosmic magnifying glass, offering glimpses of ancient galaxies as they were billions of years ago, during the universe's formative epochs. However, observing these faint distortions is no simple task. Because Andromeda is relatively close to us, its own starlight, dust, and gas can overwhelm the delicate signals of background galaxies being lensed. To overcome this, astronomers employ sophisticated algorithms that filter out foreground interference and isolate the subtle warping patterns caused by gravitational lensing. These techniques have revealed astonishing insights. In some instances, individual stars within Andromeda serve as microlenses, briefly magnifying the light of even more distant stars. This phenomenon, called microlensing, can uncover hidden objects, from rogue planets and isolated black holes to elusive clumps of dark matter drifting silently through the galaxy. Microlensing has already proven its worth in detecting planets beyond our solar system, and researchers hope that similar events in Andromeda may one day reveal entire planetary systems orbiting stars in another galaxy. If confirmed, it would mark a monumental leap in our understanding of planetary formation on an intergalactic scale. Beyond the promise of discovering alien worlds, gravitational lensing holds another, perhaps even deeper significance. It can test the very laws of the cosmos. Light that passes through a gravitational field doesn't just bend, it slows. This results in minute time delays between multiple images of a lensed source, especially if that source is variable, like a flickering quasar. By measuring the differences in arrival times, scientists can refine calculations of the Hubble constant, the number that tells us how fast the universe is expanding, and explore the very geometry of spacetime itself. Yet some questions push even further into the realm of imagination. What if Andromeda doesn't merely magnify light, but connects it? Theoretical physics entertains the possibility of wormholes, hypothetical tunnels through spacetime that could link two distant regions of the universe. Arising from Einstein's equations of general relativity, these Einstein-Rosen bridges might offer a shortcut between galaxies, making it theoretically possible to travel from the Milky Way to Andromeda in an instant, bypassing the vast gulfs of conventional space. But such a wormhole, if it existed, would be inherently unstable. To keep it open would require exotic matter with negative energy, something yet to be discovered, and perhaps impossible within known physics. Even if such a passage could be created and stabilized, navigating it would pose overwhelming challenges. The mouth of a wormhole might be surrounded by deadly radiation or gravitational forces so intense that no spacecraft could survive entry. Inside, the tunnel could twist and stretch space in unpredictable ways, potentially tearing apart anything that tried to pass through. And if time itself is woven into the structure of a wormhole, as general relativity allows, it could lead not only across space but also across time, raising profound questions about causality, paradoxes, and the fundamental nature of reality. Though no evidence for wormholes has been found, scientists continue the search, looking for gravitational signatures that deviate from those of black holes or analyzing unusual light distortions that might signal a passageway between distant points in the universe. Some even speculate that certain black holes might hide such gateways, waiting for the right conditions to reveal them. Other ideas, like cosmic strings, ultra-thin filaments of primordial energy, offer alternative possibilities for shortcuts through the universe. These concepts remain purely theoretical, but they ignite our imagination, compelling us to keep searching. After all, the universe is full of surprises. And Andromeda, with its quiet light, its magnetic fields, its hidden planets and ghostly whispers, may hold more of them than we dare to dream. Beyond the mystery of wormholes lies another tantalizing possibility: cosmic strings. These hypothetical structures, believed to be ultra-thin, high-energy filaments left over from the early universe, may hold the power to reshape spacetime itself. If two such strings were to move past each other at immense speeds, some theories suggest they could warp spacetime enough to create shortcuts between distant regions, offering a radically different alternative to the traditional wormhole. Unlike tunnels through space, these would be seams in its very fabric, natural, transient corridors formed not by engineering, but by the relics of creation. Still deeper within the quantum realm, another provocative idea emerges: the possibility of tiny wormholes flickering in and out of existence at microscopic scales. According to some interpretations of quantum gravity, spacetime isn't smooth. It foams and churns at the smallest scales. In that chaos, minuscule wormholes might form momentarily before collapsing back into the void. While far beyond our current reach, this concept inspires a bold speculation that an advanced civilization might one day learn to stabilize and expand these quantum gateways, transforming them into functional passages between stars, or even galaxies. Such feats, of course, remain far beyond humanity's present capabilities. But in theory, if a civilization could master exotic forms of energy, particularly negative energy, a requirement for stabilizing a wormhole, it might be able to bend space not just conceptually, but practically. Theoretical models suggest that under such conditions, it could become possible to create, sustain, and even navigate an artificial wormhole. If shortcuts through spacetime truly exist, it forces us to ask a deeper question: could the cosmos be interconnected in ways we've yet to comprehend? Some theories imagine our universe as part of a vast web of spacetime tunnels, a hidden infrastructure linking not just galaxies, but perhaps entire parallel universes. Though these ideas remain speculative, the pursuit of their possibility continues to advance our understanding of gravity, quantum mechanics, and the fundamental nature of reality. Even if wormholes are never detected or built, their study has already enriched physics, offering insights into how the universe bends, moves, and evolves. And as we peer into Andromeda, we naturally wonder, could life exist there? The ingredients for life as we know it remain consistent across the cosmos. A stable orbit, a location within the habitable zone, where temperatures allow liquid water to exist, and an atmosphere capable of sustaining complex chemistry are essential. While these criteria are relatively well understood when studying exoplanets within our own Milky Way, applying them to Andromeda introduces new challenges. Its sheer distance makes direct observation of individual planets nearly impossible with today's technology. Yet by examining Andromeda's structure, its stellar population, and models of planetary formation, astronomers can make educated projections. One key indicator of habitability is the presence of metal-rich stars, those that contain elements heavier than hydrogen and helium. Such elements, forged in the hearts of stars and dispersed through supernovae, are essential for forming rocky planets and the organic molecules that life depends on. Andromeda's diverse stellar population, blending young, hot stars with older, cooler ones, suggests ongoing planetary formation. This diversity parallels the Milky Way, hinting that rocky planets likely exist in stable orbits, especially in the galaxy's quieter outer arms. However, Andromeda's past is not without turbulence. Galactic mergers and interactions have shaped its present structure. These cosmic collisions, while essential for star formation, can destabilize planetary systems, altering stellar orbits, generating intense radiation, or even flinging planets into deep space. In the galaxy's dense central regions, such chaos may still linger. Gravitational forces, radiation bursts, and stellar overcrowding make long-term planetary stability unlikely. In contrast, the outer spiral arms offer a more hospitable setting. Hey, planets could maintain consistent orbits for billions of years, time enough for life to take hold and evolve. In our own galaxy, we've found planets with surface water, as well as icy moons with subsurface oceans warmed by internal heat. These findings suggest that life might thrive even beyond traditional habitable zones, protected beneath layers of ice, hidden from the harshness of space. But identifying such worlds in Andromeda is vastly more difficult. The resolution needed to detect atmospheric water or thermal signatures at that distance exceeds current capabilities. Nonetheless, scientists continue to push the boundaries, dreaming of future instruments that might analyze exoplanet atmospheres in nearby galaxies, searching for telltale signs of life. What might we find? Some researchers speculate about life forms based not on carbon, but silicon, capable of surviving in extreme environments toxic to Earth-based organisms. Given Andromeda's wide range of star types, from red dwarfs to massive blue giants, its planetary environments likely span a dramatic range of temperatures, radiation levels, and chemical compositions. Planets with thick atmospheres rich in ammonia or methane could support entirely unfamiliar biochemistries. If such worlds exist, they would stretch our definition of habitability and challenge us to reconsider what life might look like. Within the Milky Way, astronomers already search for biosignatures, chemical imbalances in exoplanet atmospheres that hint at biological processes, such as the co-presence of oxygen and methane. While detecting such signatures in Andromeda remains beyond our grasp, future technology could allow us to do just that, revealing worlds where life is not only possible, but perhaps already flourishing. Even more compelling is the idea of finding signs of intelligent life. An advanced civilization in Andromeda might leave behind detectable footprints, intentionally or not. Just as SETI listens for radio waves from distant stars, astronomers have proposed scanning Andromeda for artificial signals, laser pulses, coordinated transmissions, or even megastructures like Dyson spheres designed to capture stellar energy. If such structures existed, they might emit infrared signatures, detectable by sensitive instruments as anomalies in the stellar light. Yet the search faces daunting obstacles. The vastness of Andromeda makes it difficult to isolate signals, and alien technologies may be so different from ours that we wouldn't recognize them even if we were looking right at them. And then there's time. Andromeda has been forming stars for billions of years, much longer than complex life has existed on Earth. If intelligent life emerged early there, it might be far more advanced than us today, all long gone. Civilizations may rise, thrive, and vanish before their signals ever reach us. Still, we search, because in the silence of space, even the faintest whisper, a flicker of an unnatural light, a shadow across a distant star, a pattern in the noise, might be enough to change everything. And perhaps, as humanity dreams of venturing beyond our cosmic neighborhood, a question lingers. What if one day we reach Andromeda ourselves? The Andromeda Protocol, a theoretical blueprint for humanity's expansion beyond the Milky Way, could serve as our guiding framework for the greatest migration ever imagined. It would map out each critical phase, from initial reconnaissance missions to the eventual establishment of self-sustaining colonies in a distant galaxy. The first and most formidable step would involve developing propulsion systems capable of traversing intergalactic distances, an endeavor that dwarfs all past achievements. Reaching Andromeda would demand breakthroughs in propulsion science, possibly antimatter engines, or speculative technologies like the Alcubierre warp drive. Before humans ever set foot there, the initial phase would likely involve sending advanced robotic probes, designed to autonomously gather essential data about Andromeda's planetary systems, star clusters, and potential threats. These probes would need sophisticated artificial intelligence, capable of real-time decision-making and adaptation without Earth-based input. Communication across such distances might utilize quantum entanglement or other yet-to-be-realized techniques to send data back home. Once promising locations are identified, self-replicating robotic factories could be dispatched to begin constructing the infrastructure required for human arrival. Using nanotechnology and advanced 3D printing, these machines would extract raw materials from asteroids or planetary surfaces and build everything from space habitats to solar energy collectors. Some of these systems might even begin pre-terraforming efforts, altering planetary atmospheres using engineered microbes to produce oxygen or neutralize toxic compounds, preparing alien worlds for future colonists. Transporting humans to another galaxy would be among the most complex undertakings of the entire protocol. Unless faster-than-light travel is achieved, such a journey would take tens of thousands, perhaps millions, of years. This means colonists may live aboard colossal world ships, self-sustaining spacecraft housing entire generations. These ships would support full ecosystems, educational systems, and manufacturing centers, allowing human culture to evolve during the voyage, completely detached from Earth. Alternatively, future technologies might allow human hibernation for centuries, reducing the psychological and logistical burdens of interstellar travel. Another radical solution is mind uploading, digitally preserving human consciousness for transmission and later embodiment in artificial bodies or cloned organisms upon arrival. Upon reaching Andromeda, initial settlements would likely begin as orbital stations near resource-rich systems. These hubs would coordinate exploration, house incoming settlers, and manage terraforming operations on target planets. Establishing closed-loop ecosystems would be essential, given the impossibility of real-time support from Earth. Artificial biospheres, genetically engineered crops, and synthetic life support systems would allow these colonies to survive, and perhaps flourish, independently. Over time, these human societies could evolve culturally, biologically, and politically into forms completely unfamiliar to us today. Cut off from Earth, they might develop their own philosophies, identities, and structures, shaped by alien environments and the challenges of their new home. Should intelligent life already exist in Andromeda, humanity would face unprecedented ethical and diplomatic challenges. The protocol would need clear principles for first contact, prioritizing caution, respect, and non-aggression. In the worst-case scenario, territorial conflicts could arise, requiring defensive technologies and strategies to protect colonies from both cosmic hazards and potential hostile civilizations. Despite the risks, the colonization of Andromeda would mark a milestone in human evolution. It would signify the transition from a planetary species to an intergalactic one. This leap, technological, cultural, and philosophical, would redefine what it means to be human. It would test our imagination, our resilience, and our ability to thrive in a universe far stranger and more vast than we've ever known. At the heart of this transformation lies technology, and among the most vital tools are next-generation telescopes. Ground-based observatories like the extremely large telescope ELT in Chile represent the cutting edge of optical astronomy. With a 30-meter mirror, the ELT is designed to detect faint signals and capture high-resolution images of galaxies like Andromeda with unprecedented clarity. Using adaptive optics to counteract atmospheric distortion, these instruments will allow astronomers to peer deeper into the cosmos than ever before, searching for distant exoplanets, star clusters, and possibly signs of life. As we improve our tools and sharpen our understanding, the Andromeda dream draws closer, not just as a distant concept, but as a future that may one day unfold among the stars. Modern telescopes now produce images nearly as sharp as those taken from space. However, space-based observatories still offer unmatched clarity, free from the blurring effects of Earth's atmosphere. Among them, the Hubble Space Telescope has been pivotal in unlocking Andromeda's secrets, capturing breathtaking images that reveal its intricate structure and star formations in extraordinary detail. Building on Hubble's legacy, the James Webb Space Telescope, JWST, has pushed observational boundaries even further. Unlike Hubble, which focuses primarily on visible and ultraviolet light, JWST is optimized for infrared astronomy. This allows it to peer through vast clouds of cosmic dust and reveal regions of star formation, exoplanets, and the earliest galaxies in the universe. In the case of Andromeda, JWST has illuminated its hidden stellar populations and mapped the turbulent movement of gas within its spiral arms. In parallel, the upcoming Square Kilometer Array, a vast network of radio telescopes spread across continents, promises to become one of the most powerful tools for studying extragalactic structures. Unlike optical telescopes, radio observatories can function under cloudy skies and even during daylight, offering near-continuous observation of cosmic phenomena. They'll enable astronomers to track how Andromeda's stars and interstellar materials evolve over time, painting a dynamic portrait of its galactic behavior. Spectroscopic instruments add another layer of insight. By splitting light into its component wavelengths, spectroscopy reveals the composition, temperature, motion, and age of stars and gas clouds. The KEK Observatory, for instance, employs high-resolution spectrographs to measure the velocity of stars near Andromeda's core, helping to confirm the presence of its supermassive black hole. Spectroscopy also enables researchers to distinguish between different generations of stars, tracing the galaxy's long and complex evolutionary history. The Gaia Space Observatory has revolutionized our understanding of the Milky Way by measuring the positions and movements of over 1 billion stars with extraordinary precision. Now, similar techniques are being applied to Andromeda. By tracking the motion of individual stars, scientists can reconstruct its past interactions with smaller galaxies, identify stellar streams from ancient mergers, and predict its future evolution. Massive astronomical surveys, such as those conducted by the Vera C. Rubin Observatory, generate images of millions of galaxies. These vast datasets are too large for manual analysis, so artificial intelligence and machine learning have stepped in. AI algorithms can identify anomalies, classify galaxies by shape and brightness, and even predict gravitational interactions that could lead to future mergers. In Andromeda's case, machine learning is already helping to uncover faint tidal streams, evidence of past galactic cannibalism. Gravitational wave astronomy is opening another window into galactic events. Instruments like LIGO and Virgo have already detected the ripples in spacetime caused by the merger of black holes and neutron stars. Future space-based observatories, such as the proposed Laser Interferometer Space Antenna (LISA), could detect gravitational waves from even larger cosmic events, including the merger of supermassive black holes. If Andromeda's central black hole were to collide with another giant, the resulting gravitational wave would provide unprecedented insights into the mechanics of galaxy-scale interactions. Yet another emerging frontier is neutrino astronomy. Neutrinos are nearly massless particles that pass effortlessly through ordinary matter, making them difficult to detect but extremely valuable. They are produced in extreme environments, like supernovae and near black holes, and can reveal processes invisible to light-based telescopes. The IceCube Neutrino Observatory in Antarctica has already captured high-energy neutrinos from distant galaxies. As future detectors become more sensitive, they may detect emissions from within Andromeda's core, shedding light on its most energetic and enigmatic regions. Looking forward, next-generation space telescopes promise even more profound discoveries. Concepts such as the Habitable Worlds Observatory and the Louvre, Large Ultraviolet Optical Infrared Surveyor, aim to image exoplanets, explore galactic formation, and possibly detect biosignatures in distant solar systems. These instruments will deepen our study of Andromeda and galaxies beyond, offering a clearer view of the universe's history and our place within it. Still, many mysteries remain. One of the most puzzling involves Andromeda's dark matter halo. Like the Milky Way, Andromeda is surrounded by an invisible envelope of dark matter, which exerts a gravitational pull on stars and galaxies. However, recent observations suggest this halo may be unevenly distributed. Some regions seem to contain far more dark matter than others, challenging current models and prompting a re-evaluation of what dark matter is and how it behaves. Another enigma lies in the shape and behavior of Andromeda's spiral arms. Unlike those in our Milky Way, Andromeda's arms exhibit unusual structure and motion. Some astronomers believe these features result from past galactic collisions, while others propose internal processes within the galaxy's disk. Ongoing observations from telescopes like Hubble and the upcoming Nancy Grace Roman Space Telescope may reveal the origins of these patterns, offering a clearer narrative of Andromeda's development over billions of years. Adding to the intrigue is the sheer number of globular clusters orbiting Andromeda, over 500, more than twice as many as those in the Milky Way. These densely packed groups of ancient stars may be remnants of smaller galaxies that Andromeda absorbed over time. Alternatively, the galaxy may simply be more efficient at forming such clusters. Studying their distribution and chemical makeup could provide clues about Andromeda's long history of galactic mergers and star formation. At the heart of the galaxy lies another mystery, its supermassive black hole. Despite being similar in size to the Milky Way, Andromeda's central black hole is significantly more massive. Scientists are still uncertain why this is the case, or how it affects the surrounding stars and gas. Radio and X-ray observatories may eventually capture the violent processes around this black hole, revealing the forces that shape the galactic core. Perhaps the most tantalizing question of all is whether Andromeda has already begun interacting with the Milky Way. While a full collision is billions of years away, some scientists believe the galaxy's halos of gas and dark matter are already touching. If true, this would mean the early stages of their eventual merger are already underway. Future space telescopes may detect subtle movements of intergalactic gas that confirm this hypothesis, or challenge it entirely. Recent studies also suggest that Andromeda has undergone dramatic cycles of star formation, periods of intense activity followed by long stretches of relative quiet. These rhythms are etched into its stars and gas clouds, waiting to be decoded. Each new observation, each unexpected discovery, brings us closer to understanding this magnificent galactic neighbor. Some models propose that these bursts were triggered by past galactic encounters, while others suggest that they could be the result of internal processes. Mapping out the ages and compositions of stars across Andromeda's disk and halo may help piece together a clearer timeline of its formation. Galaxies are not isolated objects. They exist within a vast structure of filaments, voids, and clusters that make up the universe. Some researchers believe that Andromeda and the Milky Way are part of a larger structure known as the local sheet, a flattened arrangement of galaxies that extends for millions of light years. Studying Andromeda's motion and position within this structure could reveal how galaxies form and move within the broader universe. Some astronomers have suggested that studying Andromeda's rotation and mass distribution might offer insights into whether our understanding of gravity is complete. Alternative theories such as modifications to Newtonian dynamics attempt to explain certain galactic behaviors without relying on dark matter. If observations of Andromeda show inconsistencies with current models, it could spark new discussions about the nature of gravity itself. Alien architectures. Megastructures in the Andromeda Galaxy. If an advanced alien civilization exists within the Andromeda Galaxy, its impact on the cosmos could be visible even from our distant vantage point. Megastructures, vast artificial constructions built on a scale far beyond anything humans have achieved, represent one of the most tantalizing possibilities in the search for extraterrestrial intelligence. These engineered marvels could reshape entire star systems, redirect energy on a galactic scale, or even manipulate spacetime itself. While no confirmed evidence of such structures has been found, scientists continue to examine Andromeda with this possibility in mind, using observational techniques that might reveal the fingerprints of alien architecture. One of the most widely discussed types of megastructures is the Dyson sphere, a theoretical construct designed to capture and harness the energy output of a star. First proposed by physicist Freeman Dyson, such a structure could take many forms. A full Dyson sphere would completely encase a star, absorbing nearly all of its emitted light, while a Dyson swarm or Dyson ring would consist of many smaller satellites orbiting the star and collecting energy. If such structures exist in Andromeda, they might be detectable by looking for stars that appear dimmer than expected in visible light, but radiate in excess of infrared energy due to waste heat. Large-scale surveys using infrared telescopes such as NASA's WISE have scanned Andromeda's vast collection of stars, looking for anomalies that might indicate large-scale energy harvesting. While no clear evidence of a Dyson sphere has been found, researchers remain open to the possibility that future missions with more sensitive instruments could detect such structures. If an alien civilization has built a Dyson sphere or similar construct, it would signify an extraordinary level of technological advancement, possibly placing it among the most advanced civilizations in the universe. Beyond Dyson spheres, other hypothetical megastructures could exist in Andromeda, each serving a different purpose. A stellar engine, for example, is a theoretical construct designed to move an entire star system by directing its energy output in a specific direction. One proposed design known as a Chicago thruster involves building a vast mirror that reflects a star's radiation asymmetrically, gradually pushing the star in a chosen direction. If such a structure were in use in Andromeda, it might reveal itself through the unusual motion of a star or group of stars that appear to be drifting in a way inconsistent with natural gravitational forces. Another possibility is the existence of artificial ring worlds, vast structures encircling a star at a distance similar to a habitable planet's orbit. Unlike a Dyson sphere, a ring world would not enclose the star completely, but instead provide an immense habitable surface along its inner rim. Such a construct could offer far more living space than a natural planet, and might be detectable by its unusual light curve, as it would periodically block part of its star's light when viewed from Earth. If an advanced species in Andromeda has built such structures, their discovery would challenge current assumptions about the limits of engineering and planetary habitability. Some researchers have speculated about even more ambitious megastructures that could reshape entire regions of a galaxy. A Matryoshka brain, for example, is a theoretical construct consisting of multiple layers of Dyson-like energy collectors designed not just for power generation, but for advanced computation. This would effectively create a super-intelligent artificial mind on a colossal scale. If an advanced civilization in Andromeda has developed such a system, it might manipulate its surroundings in ways that could be detected from Earth. Unusual electromagnetic emissions, artificial pulses of radiation, or unexplained patterns in stellar motion might hint at the presence of such an intelligence. Galactic-scale engineering could extend even further. Some theorists have suggested the possibility of manipulating black holes either for energy generation or for the creation of artificial wormholes to allow for faster-than-light travel. If such a civilization exists in Andromeda, its activities might be visible in the form of abnormal black hole behavior, perhaps unusual fluctuations in X-ray emissions or jets of energy directed in ways not typically seen in natural systems. The idea of civilizations harnessing the power of black holes is speculative, but it raises intriguing questions about the potential of life to shape the cosmos on vast scales. Another way to search for signs of alien megastructures in Andromeda is to look for objects that defy natural explanation. Large-scale radio surveys have already identified unusual signals from various regions of the universe, though none have been confirmed as artificial. Some researchers suggest that directed energy transmissions, perhaps signals used for interstellar communication or power transmission, could be detectable with sensitive radio telescopes. If Andromeda hosts an advanced civilization, it is possible that it has developed a network of artificial signals that could one day be intercepted by human instruments. Some scientists believe that a highly advanced civilization might leave behind subtle signatures rather than large obvious structures. Instead of massive physical constructs, they might use advanced nanotechnology or even manipulate the very fabric of space-time. If an alien species in Andromeda has developed technology far beyond human comprehension, its presence might only be detected through its indirect effects on natural cosmic phenomena. Changes in the expected behavior of stars or unexplained fluctuations in cosmic microwave background radiation might hint at the influence of an advanced intelligence. If a megastructure is ever discovered in Andromeda, it would represent one of the most important scientific discoveries in history. It would prove that intelligent life is not only possible but capable of reshaping the universe in extraordinary ways. Such a finding would force humanity to rethink its place in the cosmos, offering a glimpse of what might be possible for civilizations far older and more advanced than our own. Even if no megastructures are found, the search itself deepens our understanding of Andromeda and the broader universe, pushing the boundaries of what is known and inspiring future generations to continue exploring the mysteries of the cosmos. Cosmic rebirth, the re-emergence of life after galactic collisions. The collision between galaxies is often imagined as a scene of destruction where stars are thrown from their orbits, entire systems are displaced, and the gravitational pull of merging structures reshapes the cosmos. But within this chaos, new opportunities emerge. The violent interaction between Andromeda and the Milky Way will not only tear apart old formations, but will also create regions where the conditions for life may begin anew. It is a process of transformation rather than outright annihilation, where the raw materials for new worlds are rearranged, igniting the possibility of life flourishing in unexpected places. As the two galaxies collide, vast clouds of gas will be compressed. This compression triggers an intense period of star formation known as a starburst. These newborn stars will be surrounded by swirling disks of dust and gas, the building blocks of planetary systems. Some of these stars may form in stable environments where planets with suitable conditions for life could eventually take shape. Others may inherit worlds that have survived the cosmic upheaval, perhaps altered but still retaining the potential for habitability. If life already exists in one of these systems, it might endure the transition, adapting to its transformed surroundings. New planetary systems forming in the wake of a galactic collision will experience extreme conditions. The radiation levels will be high due to the abundance of young hot stars emitting powerful stellar winds and intense ultraviolet light. However, this does not necessarily prevent life from taking hold. Some of the most resilient organisms on Earth thrive in extreme environments, from deep-sea hydrothermal vents to radiation-drenched landscapes. If similar conditions exist on newly formed planets, simple life forms might arise and persist, shielded beneath thick atmospheres, underground reservoirs, or deep within oceans. The gravitational chaos of a galactic merger will also dislodge entire planets from their host stars, sending them drifting into the void as rogue worlds. Though these planets would lack the warmth of a nearby sun, they may still harbor internal heat generated by radioactive decay or tidal forces. If they possess thick atmospheres or subsurface oceans insulated by layers of ice, they could sustain life even in the absence of a central star. The collision between Andromeda and the Milky Way may scatter these rogue planets across the newly merged galaxy, some of them potentially carrying microbial life on a journey through the dark depths of interstellar space. The immense forces at play will eject clouds of gas, dust, and organic molecules into new regions. These organic compounds, amino acids, complex hydrocarbons, and other precursors to life will be spread across the galactic environment. If they land on newly forming planets or moons with the right conditions, they could seed the development of biological processes. Some scientists believe that life on Earth may have originated from such cosmic chemistry delivered by comets or asteroids rich in organic material. A galactic merger with its widespread redistribution of matter may enhance this process on a much larger scale. The Milky Way currently has a region known as the Galactic Habitable Zone, a band where conditions are neither too chaotic nor too barren for life to develop. After the merger, this habitable zone may shift as new star-forming regions emerge and older, more stable systems relocate. Some areas that were once inhospitable may find themselves in calmer environments where life has a greater chance of flourishing. Conversely, regions that once supported stable planetary systems may be disrupted, pushing potential life-bearing worlds into harsher conditions. Some planetary systems will remain relatively untouched by the chaos, continuing to orbit their host stars as they always have. If life exists on any of these worlds before the merger, it may survive the transition. Intelligent civilizations, if present, might face significant challenges in adapting to the changing galactic environment, but they may also benefit from new opportunities. A merger between galaxies could expose advanced species to new regions of space, potentially accelerating exploration, discovery, and even interstellar migration. Civilizations on the brink of collapse in one part of the galaxy may find refuge in another, carried along by the shifting cosmic tides. From destruction comes renewal. The violent dance of two galaxies merging will scatter old stars, forge new ones, and rearrange the structure of space on an immense scale. But through this chaos, life may find a way to begin again. Whether it emerges on newly formed planets, survives in hidden refuges, or travels between the stars on fragments of shattered worlds, the story of life in Andromeda and the Milky Way is far from over. The galaxy that forms from their union will be one of change, adaptation, and perhaps rebirth. And on that note of wonder, today's journey comes to an end. Leave a comment on what fascinates you about Andromeda. If you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.